Amperes law. Amperes law. First, let me give the mathematical definition and then we'll expound it with a couple of examples. Amperes law is given by integral b dot ds equal to mu 0 I. But instead of I prefer to write it as I enclosed. That is the current enclosed. Now the question is, current enclosed by whom and what is this symbol? This integral with a circle on top of it tells us that the left hand side is a line integral. Let us write it. This is called a line integral. What does this mean? This means that the integral has to be evaluated around a closed curve. That is a curve. So what is the value of the integral b dot ds if we are to evaluate this integral around this curve? And what is I? I enclosed means how much of current is enclosed within this particular loop. That is, a wire has to cross through this or pass through this surface enclosed by this particular loop. So let us do this via a particular example. Continuing to take this loop, this is called an Amperian loop. A-M-P-E-R-I-A-N, Amperian loop. Now let us add certain wires to it. So this is one wire, it is carrying a current I1. There is another current wire that goes like this. This is I2. There is another one like this. This is I3 and this is I4. Now let us ask, if this is a scenario, there is a curve, there are a couple of wires each carrying currents I1, I2, I3, I4, then what is the value of the integral on the left hand side? So the value of the integral on the left hand side can be evaluated in the particular fashion. Let us for the time being take an example of wire 2. We know that the magnetic field produced by this is in the form of circles, and if you draw a particular circle you will know that the magnetic field at any one particular surface is tangent. So this is the direction of B produced by this wire. And let us travel around the loop in an anti-clockwise direction. So if you have a watch, then clockwise is this direction, anti-clockwise is this direction. So let us traverse the loop, that is walk on this particular boundary in this direction. So at any particular instance, the tangent to the curve is ds and this angle be phi. So what the left hand side says is, if you want to evaluate this integral around the loop, then this can be written as integral b ds cos phi, where phi is the angle between the ds vector and the b vector. Now this integral is quite difficult to evaluate if it's an arbitrary loop. That means let us imagine this loop, it is of a very strange shape, and if I want to actually integrate this around this loop, it is very tough. But thankfully Ampere has said that you don't have to evaluate this integral. Instead of that, if you look at the right hand side of this equation, you will get the value of this integral automatically. So let's see what the right hand side says. This is the left hand side of the equation. Let us look at what the right hand side says. Right hand side tells you that the value of this integral is nothing but mu naught times the current enclosed by this loop. So let us see how many wires does this loop enclosed. As you can see, I1 and I4 do not pass through this loop. I mean, you must imagine a loop and a wire must pierce inside it. Only then they are called enclosed currents. You can clearly see I1 is not enclosed, so that will not enter into the right hand side. Similarly, I4 will not enter into the right hand side. So the only wires that will enter into the picture are I2 and I3. But you will notice that I2 is going in this direction upwards and I3 is flowing in this direction. So we have to assign a particular sign to these values. That means some currents are positive and some currents are negative. So how do we decide which current is positive and which current is negative? And the way you do it is using the right hand thumb rule. That is, you take your right hand and the fingers point in the direction in which you want to move about in the loop. So that is, you move in this particular fashion. And usually the way you move around the loop is in the anti-clockwise direction. You must be knowing by now that all angles, etc., everything are measured in terms of anti-clockwise direction. So if you keep your fingers in this direction, then the thumb automatically points upwards. Then whatever currents are pointing upwards will be positive and whatever currents are pointing downwards will be negative. So therefore you will see that I2 is a positive current and I3 is a negative current. So let us write what is the right hand side. Right hand side will be mu 0 times I2 is positive, I3 is negative. So now bringing the right hand side is equal to the left hand side, we get B dot ds is equal to mu 0 times I2 minus I3. So you don't have to actually evaluate this integral. If you get the right hand side, you have calculated what the left hand side is. This is very similar in spirit to Gauss's law, where Gauss's law was flux B dot dA was equal to Q by epsilon naught. So if you could calculate what the right hand side was, then you knew what the flux was passing through that particular closed surface. Similarly here, if you can get what the right hand side is, it gives you what the left hand side is. And left hand side is very tough to evaluate for an arbitrarily shaped curve. Let us look at another example. An arbitrary curve, but now let us take the surface enclosed by this to be of this form. That is, always the surface need not be this. A surface can be of arbitrary shape. What Amperes law tells us is, irrespective of what the shape of the surface is, as long as the boundary of this surface is the same, the value of the integral must be the same. Let us do it once more. Let us replace it. Imagine a circle in the form of a soap film. The left hand side for this particular boundary with the shaded region as a circle is the same as the same circle, but imagine like a balloon. But since the boundary is the same, the value of the integral will be the same. It is a very powerful result. I hope in your mathematics classes a proof for this particular theorem will be given. You should ask your math faculty for that. Let us see some applications of Amperes law. Maybe then it will be much more clearer. So let us do that. Applications of Amperes law. Amperes law is very useful in calculating the magnetic field if the loop has some symmetry. It is very similar in spirit to Gauss's law. Gauss's law was said to be much more general law than the Coulomb's law. Similarly, Amperes law is a much more general law as compared to the Biot-Savart's law. So let us see the applications. As an application, we need currents or wires carrying currents that have some symmetry. So as a first example of this symmetry, we will choose a long wire, and we will apply this to get the magnetic field. So let us consider a long wire. This is a long wire. The current is, this is the current I, it is flowing in the upwards direction. So I'll call this I. And we want to calculate what is the magnetic field produced by this wire at any point P that is located at a distance D. So for this, what you have to do is you have to choose a Amperian loop. And from the symmetry of the problem, you can see that if you choose a Amperian loop or an Amperian curve of radius r, a circle of radius r, where r is nothing but d, then you can apply Amperes law to this. So let us see how to apply it. What is the magnetic field direction produced by this wire? You know it is from the right hand thumb rule. B will be in this direction. What is the direction of ds? ds is also nothing but in the same direction. So therefore the left hand side becomes B ds cos phi integral, line integral. But cos phi is 0 because ds is in this direction, B is also in this direction. So I get left hand side as B ds cos 0 1. But B is constant throughout for this particular circle. So B can be brought outside. So you get B integral ds. What does this mean? This means what is the length of this particular circle, which is nothing but the circumference. So therefore we have B into 2 pi d. Now what is the right hand side? Right hand side is nothing but mu naught times the current enclosed. And we know that we are traveling in this direction, so the current is positive. So this becomes mu naught times I. This becomes equal to mu naught times I. But B is nothing but, you take this to the denominator, B equal to mu 0 I times 2 pi d. This is a formula that we derived a couple of lectures back using Biot-Savart's law, and you will remember it was quite a cumbersome derivation. Now let us look at another example again of a long wire, but we are interested in calculating what is the magnetic field for any point P inside the wire. Sometimes you will have very thick wires, you are interested in calculating what is the magnetic field at a point P that is located inside that particular wire. So let's do this. Long wire, this is example 2, long wire, we will say at internal points. Okay, so let me draw a long wire. This is the wire, it carries a current I, and we are interested in calculating what is the magnetic field at any point P inside. So let's do this once again. Let this point P, let this be the center of the circle. Let us first draw a Amperian loop, and you can see that there is a cylindrical symmetry and cross section has circular symmetry. So let this be small r, and let capital R be the total radius. Now let us apply the left hand side. Left hand side is nothing but integral B dot ds. So ds is in this direction, B is also in this direction from the right hand thumb rule. So therefore cos phi becomes 1. Therefore you have integral B ds. B is constant throughout this particular Amperian loop, so becomes integral ds. But what is integral ds? This is nothing but the circumference of this Amperian loop. We get 2 pi small r. Now let us come to the right hand side. Right hand side is nothing but mu 0 times I enclosed. But what is I enclosed? I enclosed is nothing but the current that is enclosed within this Amperian loop. Now we make a very important distinction here, or rather very important point here. We assume that the current is uniformly spread throughout this particular cross section of the wire. So let us calculate that. So the current per unit area of this wire is given by current divided by the total area of the cross section of this wire, including this. So there is current throughout the wire. And from this we want to pick up how much current is flowing in only this portion of the wire. That is very easy. Now this is current per unit area, and if you multiply it with the area of this portion, I will get the total current flowing through this particular Amperian loop, so which is nothing but pi r square. This is the right hand side. This is this is I enclosed. So now bringing the left hand side is equal to right hand side, we get B 2 pi r is equal to mu naught times I enclosed is nothing but pi cancel, I r square divided by r square. Bring this to the denominator. This becomes mu 0 by 2 pi I enclosed r square divided by r square into small r. Small r cancels. As a final result we get B equal to mu 0 I divided by 2 pi r divided by r square. Now you will notice that when small r is equal to capital R, this reduces to this particular formula. That is, on the surface of the wire, magnetic field is nothing but mu 0 I divided by 2 pi capital R. Let us plot this particular function and see how it varies. So we had a formula of this particular type. B is equal to mu 0 by 2 pi r divided by r square. Now looking at figure 33.33, we can notice this is a value r and this is B. As you can see, if r is the variable, all these are constant. This is of the type k into r. So this is like y equal to mx. So it will be a straight line up to small r equal to capital R. So it will vary as small r equal to capital R. Once small r becomes greater than capital R, you will see that it falls off as 1 over r. So therefore it falls off as 1 over r. So this is like 1 over r, this is like r. There is a slight curve to this. You can check. This is figure number 33.23.